Tēnā koutou, tēnā koutou, tēnā koutou katoa. And welcome distinguished guests, dignitaries, colleagues, and our community, including those joining us remotely through Zoom. And I welcome you, particularly Ada, and our speaker, which I'm going to introduce you later. But it's great to have a family here, and my family and I joined university almost 100 days ago, and we are so delighted to be here. And also, I'm so delighted to introduce this speaker tonight on behalf of my Vice Chancellor, who couldn't do that for some reasons. Today we are celebrating 17th annual ST Lee Lecture in Antarctic Studies. My name is Ehsan Mesbahi. I'm the new Pro-Vice Chancellor for the Faculties of Science, Engineering, Architecture and Design Innovation. And I couldn't be happier to standing here tonight and to have the pleasure to host you and host our great speaker. I would like to extend particularly warm welcome to Professor Andrea Dutton, who's going to entertain us tonight with a fascinating lecture that I have no idea how you're going to connect the Antarctic to polar ice. This is the tropical tales of polar ice, and I'm desperate to know what you're going to tell us tonight. Professor Dutton is here tonight because of the generosity of Dr. Lee Seng Tee, for whom the lecture series is named after. Dr. Lee has supported a number of prestigious universities throughout the world, including Oxford, Cambridge and Harvard, in building libraries, offering fellowships and hosting annual lectures. He has an extraordinary record of philanthropy and support for education and learning that spans several decades. Dr. Lee received an honorary Doctor of Literature from Teherenga Waka, or Victoria University of Wellington, in 2006. The university is grateful for his continuing support and his efforts to foster excellence in education and research. Events such as this lecture contribute to the world-leading scholarship undertaken by the university's Antarctic Research Centre in their goal to better understand Antarctic processes and their influence on the global climate system. The university's involvement in Antarctic research goes back over 60 years, with the staff students venturing to the continent to conduct research every year since 1957. The Antarctic Research Centre was formally established in 1972, providing a platform for our scientists to lead the way in developing drilling systems to extract geological samples and better investigate ancient climate changes to the Antarctic continent. The Centre also offers teaching and government advisory services, with several staff involved in prominent international efforts such as the Intergovernmental Panel on Climate Change. More recently, the Centre has become a global leader in the computer modeling of glaciers and ice sheets in response to climate change. It has grown to be recognized as a world leader in Antarctic science and a key player in major research operations. It attracts significant government investment and interest. The Antarctic Research Centre's work contributes significantly to the university's effort to enhance resilience and sustainability, maintain research partnerships with local and global organizations, and contribute to the resolution of some of the most pressing challenges facing the world today. The annual ST Lecture is an important event in the Centre's calendar. It provides a valuable opportunity to hear from an internationally renowned guest and to celebrate the successful research and collaboration programs being undertaken by our scientists. Professor Dutton is an expert in past climate and sea level change. Her main research focuses to establish the behavior of sea level and polar ice sheets during past warm periods to better inform us about future sea level rise. She combines a range of disciplines from geophysics, to coral reef ecology to complete her work. She is also active in science communication, working to share her research with the public and featuring frequently in the media. After an extensive academic career, spanning both in the United States and Australia, she is currently a professor in geoscience at the University of Wisconsin-Madison, where she has taught and supervised the students at all levels, supporting them to achieve a variety of qualifications and receive numerous grants and awards. She is also a Fellow of Geological Society of America, was named as one of Rolling Stone's 25 People Shaping the Future, was recently named a MacArthur Fellow, and was the recipient of a US Fulbright Scholarship to come to New Zealand and the Antarctic Research Centre. She has published extensively in high-profile journals, including several publications in Science and Nature. And all of us know how difficult it is to publish in those two journals. So in my conversation with our guest speaker tonight, I tried to encourage her not to leave New Zealand next week. I don't know how successful I was, but I keep trying. And I told her that I would welcome her back in any shape and form, or any way that she would feel comfortable. You're an asset, you're a scientist, and you're a sense of pride for wherever you go. And we hope that we would be able to have that pride for a longer time. Ladies and gentlemen, please join me in welcoming Professor Andrea Dutton to the podium. Thank you.
Okay, thank you for that very nice introduction. I have felt very welcome here my entire time in New Zealand, even despite the lockdown. And I would like to thank Dr. Lee for making this lecture series possible. I would like to thank Rob Mackay for inviting me to give this lecture this year, and his predecessor, the earlier director of the Antarctic Research Centre, who invited me a few years ago, and I said, can I take a rain check? I'm hoping to come for longer. And so I also would like to thank Fulbright New Zealand for making that possible and for sponsoring my trip out here to spend more time with my colleagues here at Victoria University. So this evening I'm going to spin you some tales to tell you how the tropics are related to polar ice sheets. And I often joke with my colleagues here that while they're being intrepid explorers going down to the ice, that I get to go gallivanting around tropical islands to learn something about the Antarctic ice sheet because we can see the signal of sea level rise as the Antarctic ice sheet melts in the tropics. And so to kick things off, I'm actually going to introduce you to myself and to my work with a quick 2-minute video that gives you a sense of what it is that I do as a field geologist, and it will also give you a sense of why what I do is important and how it relates to that. Sometimes people think of the work I do as trying to save the planet. I'm not really concerned about the planet. I'm a geologist, and the planet has been here about 4.5 billion years. And the planet's going to survive sea level rise. It's still going to be here. The question is, though, how are we going to survive? And one of the things we need to know in order to prepare is how quickly is this process going to unfold? And one way we can answer that question is by looking at Earth's past. Because to some extent, the Earth has done this experiment for us before. We're looking at this by studying fossil coral reefs. Corals grow near the sea surface because they need the sunlight to survive. And so we use them to track the position of sea level in the past. Coming to the University of Florida was a really natural choice for me. It's a collaborative environment within departments, within the college, between different colleges in the university, and all those things have a great appeal. We're building an incredible depth of knowledge about what's happening to our planet. And one of the things that we can do is use this information to help us to create a new future. A future that we want to be a part of. Right, so I should have mentioned, also it wasn't mentioned in my introduction, that the last 9 years I've been at the University of Florida, in case you picked up on that. So they made that as a promotional video. But it's really a quite nice explanation of what I do. And it's a nice way for you to get to see the work that I do as a field geologist. Give you a little bit of background on how that works. So this is the world that we are now living in today. And in your program, if you had a chance to look at it, it says human experience is shaped and sometimes forever altered by the extremes we experience in our lifetimes. And we are now living through an era of rapid global warming that brings with it new extremes that impact our lives and our livelihoods in a myriad of ways. And I used to say that one of the most visual impacts of that climate change is sea level rise, where you can actually see the inundation. It's very hard for people to understand. It's very abstract when you talk about 2 degrees of warming. Well, what is that? You know, it changed by 10 degrees today. Whereas sea level is very visual. But now we have these images from wildfires, such as this one here from earlier this year in Australia, which are perhaps even more striking and profound. The one on the right, if you haven't seen this one before and can't see it quite in the picture, in the middle here, there's a big white octopus sitting in the middle of this parking garage that was photographed in Miami Beach during a normal high tide. This was not a storm surge, it's kind of king tide season, normal high tide. So you have to ask yourself, you know, at what point are we going to realize that this is not right? You know, maybe humans shouldn't be occupying this space that the ocean is taking back over. And the reason that all of this is happening is displayed at the top of the screen here now. These color stripes that maybe many of you have seen before, called global warming stripes, actually show the temperature change on a color scale from the late 1800s to present day. And you can see it's a very striking visual image of how rapidly we have been warming our planet. And when you look back over your lifetime or the lifetime of your parents or your grandparents, you realize how that really cannot be used as a baseline for what is happening today at all. And that is an important perspective for us to keep in mind. But when you hear stories about sea level rise, they're often accompanied with pictures, images like this, of ice sheets, polar bears. And it gives you the impression, the false impression, that this is a distant problem and it's far away and it doesn't really affect us because, you know, who's going to go to the Antarctic ice sheet? Well, I say that, but there's several people in the audience who have, of course. But I find it's more effective and to convey the real reason why this issue is important is because of the way it will affect our lives as we know it. And so in telling this story, we really need to put humans literally into the picture. And so this is perhaps a more visually striking image. And what is shown here are 4 people who are standing in water at a depth that it's going to reach within their lifetimes at the place where they live. So these are 4 different locations in the US that they've considered for this particular image. And this really hits home a little bit more, doesn't it, than looking at a picture of a big white ice sheet. This is why we are worried about the issue of sea level rise that is already happening today. So the real question is then to pose to us scientists as well, how quickly is this going to happen? If we're going to plan for this, to adapt, we need to understand how quickly this process is going to play out. Now that's challenging because we've never lived through a climate that's warmer than today, and so we haven't experienced that, and we don't know. We don't understand all the physics of the retreat of these ice sheets to tell you exactly how quickly that process will happen. And so that's where my job comes into play. And as a geologist, we can look back at time, as I explained in the video, and look at examples of past warm climates to try to understand when the Earth warmed before, how quickly did those ice sheets retreat, and how sensitive were they to the warming? How much did they retreat, or were they not really affected by the amount of warming that we're expecting? So those are the types of questions that we can ask as geologists to help us to better plan for the future. So today I'm going to take you back in time to a time period that I've been working on that is known as the last interglacial, which is denoted here by the pink arrow. So you're looking at a graph of sea level on the vertical axis that goes back in time, and these are thousands of years, so 100,000, 200,000, and so forth. And you can see there are these natural cycles that occur about every 100,000 years in sea level, and those correspond to changes in temperature and ice volume. So as the ice sheets melt, sea level goes up, and as the ice sheets grow, sea level goes down. So if we go back in time from today, this is the last glacial period about 20,000 years ago, where we had large ice sheets in the northern hemisphere. And then before that, there was a warm period back here, which we creatively call the last interglacial. It's between the glacial periods, right? So that's where that name comes from. So I was reflecting on this last week when I was giving a talk to some of my colleagues here that more than 50 years ago now, there was this fellow named John Mercer who published a paper in a rather obscure little journal, and it was about Antarctic ice during this time period, the last interglacial. Here it's referred to as the Sangamon period. He found evidence of sediments in Antarctica that indicated that summer temperatures were some 7 to 10 degrees Celsius higher than today at some point during the Pleistocene. Now, the Pleistocene is more than 2 million years long, so it's notoriously difficult to date sediments in Antarctica. So all he could say is, well, sometime in this time period, we think that perhaps the West Antarctic ice sheet collapsed and we had open water here with these warm summer temperatures, and that would have risen sea level by about 4 to 6 meters. And he said, well, there's evidence from the last interglacial that sea level was higher, so perhaps that's when this happened. And so he put forward this hypothesis more than 50 years ago. And so I think it's an appropriate point of time for us to now take stock in what have we learned in the last 50 years? What can we say? Was he right? And what have we learned about the Antarctic ice sheet in the intervening time? A whole heck of a lot is what I can tell you. So on the left side of this image is the very first composite satellite image that was put together for Antarctica back in 1964. The image on the right side of the screen, though, is an image of 3 different data sets, modern data sets that are superimposed upon each other. There's the topography data set, the DEM, that you can kind of see in the 3D shading. There's the sea ice extent, which shows the sea ice extent for a particular day in mid-May, several years ago now. And the colors that are plotted over the continent show you the amount of warming over about a 50-year period that has occurred over the Antarctic continent from a data set that they've analyzed over that time period. You can get daily updates of satellite images from Antarctica now. So it's really profound, the data explosion that we've had over this time period. And at the same time, we've also been on the ground and in the ocean trying to learn what we can about the ice sheet and the land beneath it, and the oceans and the marine sediments that border the continent that can also tell us something about what's happening on the Antarctic continent. But it is very difficult to do field work in that region, and there are only a few places where we've punched holes into the ice sheets or that we've penetrated to beneath. And so we do rely a lot of times on these airborne data sets that in a way can fill in some of the picture and interpolate in between a bit better. So over this time period, Antarctica has been melting. And more recently, that melt rate has accelerated. This graph shows you on the vertical axis sea level rise in millimeters and time from 1993 over almost to present day. This is a satellite data set. It only goes back to 1993 because that's when these missions started to plot it that way. And over this time period, the average rate of rise is only about 3 millimeters a year. Sounds awfully small. And you may wonder, why are these scientists so worked up about 3 millimeters a year? And it has to do with a couple things. One is that it's been rising for longer than this, and I'm going to show you the plot over the last century in just a moment. But also that we've been building infrastructure right on the edges of our coastlines, and there is no capacity for us and we're starting to tip over the edge in many places that are getting more frequent coastal flooding. So when we put this in context of the last century, there are only about 4 graphs in this talk. I think you've seen 3 of them already, so don't worry, it's not going to be a talk full of graphs. So here's the vertical axis again in millimeters, and calendar year from 1900 to about 2010, I believe. So this shows you the record that we have from tide gauges. Now, tide gauges were first installed to measure the tides, not to measure sea level rise. But it turns out, while they sat there and seas went up, they became an excellent recorder of what was happening with sea level rise. There are 3 different lines on this graph. That's because there were 3 different research groups that analyzed the same data set in different ways. I could spend a whole hour talking about that, but fortunately you haven't come to that talk today. You don't have to worry about those details. As you go back in time, the lines tend to diverge because there are not very many tide gauge records that go back that far, so it becomes harder to interpolate what the global average is. But regardless of which line you look at, sea level has clearly been rising by about 20 centimeters over this time period, and it's been accelerating, again, regardless of which of those curves you look at. And the dominant contributors to that sea level rise signal are the thermal expansion of the water as it heats up and it expands, and the melting of mountain glaciers. Now, at the same time, Greenland and Antarctica were melting as well, but they were not the dominant reason for that signal in the 20th century. More recently, the melt rate from the polar regions has been accelerating, though. And as we look into this next century, mass loss from the polar ice sheets is expected to exceed these other contributions to sea level rise. So it will become the dominant player here under future warming. So it is imperative that we understand how these large ice sheets will respond to that warming. People used to think that these ice sheets were so large that it would be really hard to perturb them. They were kind of sleeping giants. Well, it turns out we've woken those giants up. And so now it's our job to figure out how quickly that process will unfold. When you hear about melting in Antarctica in the news, you may often hear something about the West Antarctic ice sheet. And that is on the left side of this diagram here that gives you a little bit of relative size of this very large East Antarctic ice sheet and the West, which is connected, but this is lower down. When you look at an overhead map view of this, this has some data that's superimposed, and these big red dots are showing you places where you have a lot of mass loss, a lot of ice coming off of Antarctica here. The larger the dot, the larger the flux of ice that's coming off here. So the West Antarctica is already showing signs of speeding up and of melting here. And the reason that scientists are so worried about West Antarctica is because most of it is what we call marine-based. That means the bottom of the ice sheet actually sits below sea level. So the weight and the thickness of all that ice presses down on the surface of the Earth, and now the bottom of that ice sheet is sitting below sea level. And that means as the waters warm around the Antarctic continent, they're basically warming the underbelly of the ice sheet, and it is susceptible to very rapid retreat because of that geometry that it has there. So when we run the ice sheet models with warm temperatures, we often get results that look something like this, where we've lost large portions of the West Antarctic ice sheet. Those are these marine-based sectors that are very susceptible to retreat. And that is what we are worried about as we move into the future. And it remains essentially the largest uncertainty in sea level rise projections. How is the West Antarctic ice sheet going to respond to future warming? Understanding what the tipping point for it then is, what's going to set off this process where it starts to collapse is very important. And that's one of the things that we'd like to learn by looking back in time. What is the climatic context? If this has happened before, we can understand how much do you need to warm the waters, say, to get this process to happen. Okay, and fortunately you've already seen the video, so you know what it is that I do and why I do it. I look at fossil coral reefs. We travel around the world. The image you saw, I meant to mention at the very beginning of the talk that's in your program, is a coral reef terrace from Western Australia. These are actually 3 more pictures from Western Australia. We've been working on parts of that coastline that have last interglacial fossil reefs that are exposed off and on over about 1,300 kilometers. So it makes a great place to go to look at this. Here we go. Here's the picture again. This particular site is actually tectonically uplifted. And so I used to avoid this site because I wanted to go to a place that was tectonically stable so I could understand how much sea level rose in the past, not a place that's been affected by tectonics, which is going to overprint that signal. But we went to visit this site one year. One of our colleagues took us there, and we knew we had to go back because what was so special about this site is that the whole last interglacial reef has been uplifted and exposed in all its glory, and I can see it in 3 dimensions. In most places, you just end up walking over the surface of it, and you can't see what's underneath. And this gave us a real chance to understand how sea level changed during that warm period. And what we're using this section for now is to understand Does that rise happen gradually? How quickly does it happen as the corals grow one on top of each other? And so that's one thing that I do is I date the timing that those corals grew to reconstruct those rates of sea level rise. And we also want to know, if it wasn't gradual, was there perhaps a big step when we had a collapse of part of an ice sheet? Or is it more like going up a staircase where we lose outlet glaciers here and there? Those are really important questions for coastal planners right now, because planning for a gradual rise is a whole different ballgame than planning for a sudden jump that might happen sometime soon. And so those are some of the fundamental questions that we're trying to answer looking at this particular section, which is still a work in progress. But I wanted to show you a couple pictures from this site because it's really gorgeous. You can see this whole section exposed, and I wanted to also credit some of my colleagues at the University of Sydney. We've been working with Jodie Webster, who's been to many field expeditions with me, and one of the students we've been co-supervising, Kelsey Sanborn, and a student of mine, Caroline, who's not pictured here, who's been working on this section. And that's me. I did some work too, drilling on the reef. This is one of the little drills that's easy for us to backpack in. You certainly can't get a truck out to this site at all, so we have to use equipment that we can carry. I did manage to break the drill on this outcrop, unfortunately, but we got a good 3-meter core out of it, which is what we wanted first. And then this particular site is Red Bluff. I don't know if any of you have ever heard of this. This is a surfing mecca in Western Australia. So this is the gratuitous shot for all the surfing experts in the audience to see the great break that was out there. So it was a bunch of surfers and us. Okay, so what I'm going to do is share with you this story in really 2 parts. One is to look at the deep past, to know what we can understand by doing this type of work. And then we're going to talk about what that means for the future, and that's part 2. So there's a group that I've been working with for many years now called PALSEA, for Paleo Sea Level. And the focus of this group was to understand the magnitude, the rates, and the sources of sea level rise during past warm periods. And so we brought together ice sheet modelers, people who, like myself, who reconstruct sea level in the field, people who reconstruct the position of the ice sheets through time, climate modelers, everyone who's looking at these questions, but from all different angles. And several years ago, we decided to write a review paper to summarize what it was we understood about these past warm periods as a community. So this is the cartoon diagram that came out of that work that I'm going to share with you today. And what you're looking at on the left side here is present day. Sea level is at 0 by definition, and this is the present extent of the ice sheets in Greenland and Antarctica. We have already warmed the planet by a little more than 1 degree Celsius relative to pre-industrial times. We've done that by ramping up this greenhouse gas concentration in the atmosphere very rapidly. Shown here to the right is this period I've been talking about, the last interglacial, about 125,000 years ago, when global average temperature was about the same as far as we can tell, yet our best estimate is that sea level was some 6 to 9 meters higher, or 20 to 30 feet for the Americans who are in the audience today, for reference. As we look at these other warm periods, we see that repeatedly, every time we warm the Earth by somewhere between 1 to 3 degrees Celsius, that sea level rose by 6 meters or more, which is telling us that, yes, these ice sheets are sensitive to what might sound like very small changes in temperature. And if this is true, it means that the ice sheets today are out of equilibrium with the present climate. The analogy I often use is it's like taking 2 ice cubes, Greenland and Antarctica, and throwing them into a hot room and then standing back and watching what happens. And that's what we're doing right now. We've heated the temperatures very quickly, and now we're watching the process of them melting and catching up to that climate state, if you will. So that was one of the main takeaways from this synthesis that we put together, is that during these recent warm periods, these small increases in global temperature meant a lot of sea level rise. Now, I just saw someone sigh very deeply in the audience. This is rather a sobering conclusion to reach. I stage this at the middle of my talk as the most depressing part, and then I try to lift you back out for the rest of it, right? So these are some maps of New York City and Florida, where I lived for the past 9 years, and I've lived in New York City as well. What they would look like with 6 meters, the low end of that estimate, 6 to 9. 6 meters of sea level rise. And this makes sense, in fact, because over here in South Florida, this was all underwater during the last interglacial. We can tell because there are shallow marine deposits all across South Florida, right? So this is pretty extreme. Now, the good news is that it's not going to happen overnight, but it could mean that we're committed to something like this in the future, even with the amount of warming that we've already had. And that's pretty profound. It means that the sea level rise that we see today is just the first step in what is going to be a very long journey of continuing coastal retreat. It's not going to stop in the year 2100, which is when you see a lot of the projections ending. At the same time, it will not be the same everywhere. It depends on where that meltwater comes from. So if you were to melt water from Greenland, it will give you a different pattern of sea level rise across the globe than it would if you melt from Antarctica, and that's what is shown here. In fact, when Greenland melts, you end up with a local sea level fall in the dark blue near to Greenland, and as you move farther away, it goes higher up, which seems very counterintuitive to most people. Like, what about gravity, right? Well, actually, it is because of gravity that this happens. So these ice sheets are so large that they have their own gravitational attraction. So the water in the ocean is attracted to the big ice sheet. As you melt that ice sheet, it relaxes that attraction some. So in the region of the ice sheet, sea level falls a bit, even though you've added water into the ocean. But are you watching what's happening to my elbow over here in the far field? As it falls in the near field, close to the ice sheet, it is rising over here. And so it turns out that in the east coast of the US, they are much more concerned about what's happening in Antarctica than Greenland. And New Zealand kind of sits a little bit in the middle. Well, you need to worry about both for sure, right? So if we look at what happened during the last interglacial, this was our assessment of trying to account which of those ice sheets was contributing to the 6 to 9 meters of sea level rise I was talking about. And that is broken down here in this diagram. So there would be some due to thermal expansion. You could melt all the rest of the mountain glaciers on the globe. That will still only get you up to about 1 meter of sea level rise. We have evidence from the Greenland ice sheet, from ice cores, from marine cores around the continent, and from ice sheet models that tell us that there was a large part of the Greenland ice sheet that did stay intact during the last interglacial. So part of it melted, but not all of it. And the best estimates are somewhere around 2 meters. So we put in 2 more meters coming from Greenland here in this diagram. And then to get up to 6 to 9 meters, by subtraction, we must have tapped into the Antarctic ice sheet, right? And that was our assessment here. And it is something like 5 meters, which sounds a little bit like what we would expect out of the West Antarctic ice sheet. But mind you, these uncertainties are quite large if you're looking at those big black lines that I've put on there. And so if you take, in fact, there was a more recent estimate, Greenland may have contributed something like 5 meters during the last interglacial. So what would that look like if we take that one study? If Greenland contributed 5 meters on top of the one that we have down here, we're already in the range of 6 to 9 meters, and we don't need the Antarctic ice sheet. Uh-oh. So what can we tell from the far field records about what happened in Antarctica? Part of the important thing here is that we can date the precise timing of when those corals grew. And it's possible that this changed during the course of the interglacial period, which was more than 10,000 years long. So it turns out that if we look at the beginning, there are some sites that suggest sea level was higher, 3 to 6 meters higher, right at the beginning of the last interglacial. Now, Greenland is known to have kicked in only towards the end of that period. So if we were already 3 to 6 meters above at the beginning, the only thing it could have come from is Antarctica. And so the plot twist here is that things may have changed over this time period from the beginning towards the end of the last interglacial, that Antarctic ice sheet may have melted and it may have started to regrow as Greenland was melting. They may have been out of phase. And it turns out there's more and more evidence emerging that that may have been the case. Now that's quite different from what we're doing today. Today we have warmed up the atmosphere with greenhouse gases and it is heating both poles at the same time, simultaneously. So you would have to kind of add these two things together in that sense. And so understanding the timing and the source of the ice sheets is a very important part of the story. And there are still a lot of details to be worked out here. And so there are some of this is still a hypothesis that's being tested in terms of the part of the beginning with the Antarctic ice sheet. Okay, you say, so, but what can you say from the tropics? Did the West Antarctic ice sheet collapse or not during the last interglacial? Was Mercer right? Did he get the story right 50 years ago? So I've put up a little diagram here to look at all the different evidence that's out there, not just the fossil reefs. We have some evidence from sediments in various places that suggest the West Antarctic ice sheet collapsed during the Pleistocene, but we don't know quite when. So those sit there in the middle because we're not sure if that's last interglacial or not. Now on the right side of this slide, I'm going to put all the studies that suggest that some sector of the Antarctic ice sheet did collapse during the last interglacial period. Here you go. Each of those dots is basically one study, except for the one down here. This is all the different suite of literature that we have on all the far-field fossil coral data that I've been talking about to you. There's data from ice cores. We have data from marine cores, where we look at the chemistry of the sediment, and we can track which bedrock it must have come from. And we know that the ice must have retreated far enough to expose that bedrock. There are also ice sheet modeling studies. There's another site where there's an absence of ice right during the last interglacial at a spot in West Antarctica, which suggests that perhaps it wasn't there at that point in time. And then there's also evidence from the North Atlantic, which is very far away, from marine sediments there. The chemistry there tells them also a story about this difference in the timing of phasing between Antarctica and Greenland, and also suggests a significant contribution from Antarctica. So all of these taken together do point to a collapse of at least some sector of Antarctica. I think all but one of them suggest the West Antarctic ice sheet, and about 5 of them or so suggest that that contribution happened early, which I would say is consistent with what we saw in the far field. So while you might look at any individual study and say, I can interpret that differently and I'm not really sure that's what that means, when you start to look at the whole picture, it starts to hold together. Now on the other side of the story, these are the 2 studies that I found that suggest it did not, that we have some evidence that really says it did not collapse. And I should mention the 2 bubbles with asterisks are ones that are not published yet, though I expect them to be published soon, and I've spoken to the authors about them. So it's not an entirely coherent story yet, but I would say the balance of evidence at this point in time certainly tips towards the interpretation that the West Antarctic ice sheet may have collapsed during the last interglacial period. So, what is the tipping point for this ice sheet? This diagram shows this warm water I was talking about bathing the underbelly of the ice sheet. And as it warms it, that will cause the ice to retreat past this grounding line. This is the point at which the ice and the water and the sediment meet together. It's pinned right now on this high point. And once it retreats past that pinning point, it can start to retreat very quickly, and you can't just reverse that process. You can't decide next year, okay, we'll stop, putting carbon in the atmosphere and I'm going to use my skateboard every day. Can't go backwards. Once this process starts, it's going to keep going. So are we past this tipping point? Are we near this tipping point? There are some colleagues of mine who would argue that we are past that tipping point already. And this is a picture of the front of the Thwaites Glacier. It was taken about a year ago, the first time any humans had been there to see it. It's one of the most vulnerable sectors of the West Antarctic ice sheet that they're studying right now. But there are people who would argue with this and say, no, we're not quite there yet either. But to me, the whole thing about tipping points is you don't really know where it is until you're past it. Right? Until you say, oh, there it was, right? It was back there when sea level started going up by centimeters a year instead of millimeters a year. The point is that we're probably very close to it, whether on one side or the other of this tipping point. Some of the modeling suggests that we still have time to stop this from happening, and that should give us impetus to do so. So that brings us to part 2, which is the future. And I've intentionally left this slide blank to remind us all that the future is still unwritten. Future is not just a place we get to go to. It's a place that we get to create together. And I think we've all learned that through this COVID crisis, that the actions that we take can change the outcomes at the end of the day. So what are some of the implications for policy with this understanding that we have from the past and from the past behavior of the Antarctic ice sheet? One is this issue of sea level commitment, right? The actions we take today, even the warming that we've already done, has committed us to a certain amount of sea level rise. But it's going to play out over long timescales. And this is just the first step in a long journey. So if you're making a plan for adaptation, it's not just to 2050 or to 2100. You need to have in mind that this is going to be an ongoing process for quite a long time. I wanted to give credit to Peter Brannon for tweeting this out. The next president of the United States he's referring to gets to set the agenda for the next few tens of thousands of years. This is not a joke, right? These actions we make today will have long-lasting impacts far beyond our lifetimes. One of the questions we are still trying to answer, though, is this what I call the nature of sea level rise, if it's gradual, if it's stepwise, if it's that sudden collapse. And that will also be very important in terms of developing the right policies. The other thing to bear in mind is sea level rise is more than just inundation. So if you build a seawall, maybe that might work for a little bit to keep the water from coming in over your home or your business, but it will not stop it from intruding into the freshwater aquifers underneath that seawall. And at the same time, that will bring up health issues in the community. You'll have stormwater problems, loss of coastal resources. You can read this list better than I can read it out to you quickly. But when you're thinking about this, you need to think about this whole picture and not just one component of it. We'll come back to some of the things on this list in a moment. But I wanted to spend a moment on this diagram. I think this is the last graph of the talk. And this is the one that the sea level scientists is probably the main tool that they hand off to coastal planners in terms of planning. They give them some type of sea level rise projection to plan for as we move into the future. This one, again, I apologize, is in feet on the vertical axis. But if you follow that red curve up to the right to 2100, it takes you to 8 feet, which is well more than 2 meters. That is hopefully a worst-case scenario that invokes some rapid retreat of the Antarctic ice sheet. The darkest blue curve at the bottom is just a linear extrapolation of the satellite data that I showed you before. But we know that sea level rise is accelerating already, so we should probably just take that linear one off because we know that it's accelerating. So people look at this and they say, well, do you really know what's going to happen? I mean, there are all these curves there. It looks really uncertain. So how are we going to plan or do anything? And they essentially use the uncertainty as an excuse not to start planning now. But I like to look at the flip side of that. Every single curve is going up, right? You can have an argument with me about how quickly I think this process might play out. And if you talk to a different scientist, they might give you a slightly different answer. But unquestionably, what we need to prepare for is a more watery future. And hence, we can't use this as an excuse to delay action in the present day. But the other comment I wanted to make about this graph is that unfortunately, I can guarantee you that sea level rise will not look like any single one of these curves. It's very unusual to hear the scientists use the word guarantee, like I just did. But that's because I know what these data look like, which I'll show you in a moment. So let's pick one of these curves to look at. I'm going to pick this one here, this green one, and say we're going to reach 2 feet by, I don't know, the year 2060 or something. It doesn't mean that we won't reach 2 feet until 2060. It means we're going to reach 2 feet with increasing frequency until we are there on average. So some people look at this and they think, oh, we have time to prepare to get to 2 feet. So really, I think a more useful framework is thinking about the frequency of coastal flooding events. This is what real sea level data looks like. Oh, sorry, there's one more graph. This is a tide gauge from Virginia Key, which is near Miami, Florida, just offshore there. Again, it's in feet on the vertical axis. Everyone knows tides go up every day. This also shows an annual signal. So the king tides that I mentioned before happen in the autumn, fall season, and it's lower in the spring. And these spikes that you see here are hurricanes. Hurricane Irene, Rita, Wilma, which all made landfall in Florida. Hurricane Sandy did not make landfall, but it went offshore and created enough of a storm surge that we had extreme sea levels. And then in the meantime, sea levels just creeping up in the back, creeping up, and then bang, 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 we get king tide, king tide, king tide at the same level that used to be only hurricane storm surge level. Now happens every year. And if you talk to the people who live there, it's not just one day. Now it's many days or many consecutive days. And at what point are you going to say, okay, if my driveway is flooded one day, that's fine. But if it's going to be 10 days, there was a community that was flooded for more than 3 months solid last year. Flooded roads. Couldn't get out unless you're on a boat, right? So now we have these extreme events are really what is going to define the future. So thinking about this in terms of frequency of coastal flooding, I think is a more useful framework. This image on the left shows in the year 2017, relative to the year 2000, more than a 200% increase in many places around the US in the frequency of coastal flooding in only 17 years. The message here is that sea level rise is going to happen faster than you think it will from just looking at the sea level projections that I showed you before. So one final story here is in Sugarloaf Key in Florida. This is a little bit north of Key West, which is down at the bottom. They did a study just this last year that was released in early December. How much would it cost to keep a single stretch of road that's 3 miles long? They're having some problems with getting it flooding now. So how much would it cost to raise the road and keep it dry throughout the year for different years, right? So this is to address this issue that some people say, oh, we can just engineer our way out of this problem, right? We can just adapt. Okay, so here's the study that tells us how much it's going to cost. $75 million to raise it 1.3 feet, which is their projection that they're using to keep it dry throughout the year. And you can see how that number blows out up to 2060, more than $180 million just for a 3-mile stretch of road. But think about what happens to the water that would have been sitting on the road. Now that you've raised it, you've pushed it off into people's yards, making the flooding worse in their houses, right? So this is not an effective long-term solution, nor is it economically viable. And what was really interesting when this study came out was that it was one of the first times I've seen the politicians say, we can't save everyone, right? This is not going to work. As the seas rise and the flooding gets worse, not everyone can be saved. So if this process is going to happen, we need to decide how we want it to play out. We can't just engineer our way out of the problem. I'm not a huge fan of the idea of seawalls at all. Not to say that there's not a place and a time for them, but a couple of those reasons are listed here. One, it exacerbates existing racial and social inequality. Only the communities that can afford to put them in will put them in. And once again, that water gets displaced. The water that would have flooded that land gets pushed out into the communities that couldn't afford it, hence making it even worse for them. It also builds in a false sense of complacency for those living behind the wall, because then they think they're safe and they upgrade their house and everything, we're fine, we're behind the seawall. But at some point, it's inevitable that the wall will be breached or it will fail. Think of New Orleans, for example. So in the long term, you really have these two options: build walls and live in a bowl, or you can retreat. There's a lot of adaptation and gray area in between, but in the long term, those are essentially the two end member options. So here's the information. I have given it to you. Now what are we going to do about it? This is a statue that someone put in Germany, and I think it's brilliant. It's a bunch of politicians standing around debating what they should do about climate change and sea level rise while the water's coming up over their ears. This literally happened last year. In Venice, all that flooding you saw in the news, this Italian council was flooded immediately after rejecting measures on climate change. Karma, right? The time has long passed for us to take action on this issue. Climate change is no longer just a vision of the future. It is here today, and it is here to stay, and it will be getting worse. So to conclude, I want to take a moment and say, what have we learned? The polar regions of our planet may seem beyond reach for most of us, but they are not beyond our influence. Despite the fact that they are very distant, we have, perhaps unintentionally, but now very knowingly, we are changing these frozen worlds in the polar regions. And when you watch nature shows on TV, they often present this argument that we should be concerned about all the changes happening because of all of the varied and wondrous forms of life. And we should. But I don't deny that's true, but I want to make a slightly different argument today, one that's perhaps a little bit more self-centered and anthropocentric, if you will. I would like to impress upon you that these seemingly sterile, vast expanses are essential to human life as we know it. And because the presence and the stability of that ice sheet is so important in dictating climate patterns and in controlling sea levels that will reshape coastlines around the world, that gives us impetus to study the Antarctic continent in past and present so we can understand its future. The good news about our experience with the COVID-19 pandemic, because we have to put a silver lining on it, right, has taught us that when a crisis stares us in the eyes, we can mobilize and control our outcome. But like global warming, we can't make COVID-19 completely disappear on planet Earth. But there are lots of actions we can take to make it a whole lot less bad than it needs to be. So in terms of global warming and climate change, that primarily means slashing our dependence on fossil fuels. And like this global pandemic, continued global warming will bring with it dire economic consequences. It will expose the weaknesses in social infrastructure, and it will hit hardest on already marginalized communities that are least well equipped to adapt and to respond. But this analogy only goes so far. There were delays in the progression of COVID-19, right? You might be infected, a few weeks later you might show symptoms, a few weeks later you might need to be hospitalized, a few weeks later you might need to die. But that meant that by changing our actions, we changed course and we saw the difference in a matter of weeks. But the time frames here are vastly different. If we wait until the impacts of climate change and sea level rise become so urgent to disrupt our lives as much as the COVID-19 pandemic did, or even worse, as it has for some people already, we can't correct course in a matter of weeks, which is why the more we do, the earlier we do it, the better off we are in the long term. Now, New Zealand is well positioned to take on this challenge, and it's already taking steps in the right direction. But those steps must grow, and they must do so quickly. So my advice to you, if I could borrow a phrase, is to go hard and go early. Thank you.
Thank you, Andrea, for that quite remarkable talk. I thought you said you were going to get positive in the second half of the talk, and it kind of just made me more terrified, to be honest. And I fully appreciate why you're moving from Florida now, after seeing that tide gauge work. I was going to say I'd love to come and work with you in Florida, but I think you're probably in a much safer place in Wisconsin. So I'm going to pass it over to the floor for questions now. So we have some people online as well. So for those that are online, just type in a question and we'll try to answer those in the order that they come through. But open the floor in the room here for questions first.
They're stunned.
Yes.
One graph you didn't seem to show was one showing the spikes in the past instead of a gradual curve rising, one with steps on it that you might have on your field gauge.
Right, so the question was, one graph I didn't show was how sea level rose in the past. Did it have steps and spikes in it as we go? I deliberately haven't even drawn a curve like that yet because I feel like there's still enough uncertainty in the data that you could fit a lot of different scenarios through it. But one of the things we are trying to do is without those individual data points, just looking at the outcrop, we can tell a lot about looking at the corals and the morphology and how they grew, actually how quickly sea level might have been rising. And we can see in some of those that I showed you the pictures of evidence for a really rapid pulse right in the middle there. And so we're using that type of information to refine our understanding, but it's hard to put a precise chronology to some of that still. Those corals at Red Bluff are all very altered and we're not getting good ages out of them. And so it's more kind of relative timing that we're talking about rather than absolute rates of rise. But that is certainly what we're working towards, is to try to have a curve like that.
It would be quite useful for planners.
Extremely useful for planners.
How big a spikes they might have if you're a drainage engineer.
Yeah, so at the same time, the analogy is not perfect to the last interglacial, and I did point out some differences already to you between that time period and what we're experiencing today. So we have to bear that in mind, but at least it can tell us something about the process of that ice sheet retreat and how we might expect it to play out and what the possible rates might be. Yes.
Yes.
Sorry, Kevin Colbert from the U.S. Embassy. Thanks again for the talk. I know that you were reluctant to say that we can't, well, you did say we can't engineer our way out of this. And I think you're saying, if I might suggest, there's no panacea, there's no sort of one solution to this complex problem. But can you give us a reason to hope, a reason to be optimistic? Is there any technological or engineering innovation that might help in some way to mitigate this? Or is there any change in behavior, specific behavior, that you can point to that would be helpful, constructive, that we could talk about, promote, and advocate?
Right. So the question I'm repeating for those of you who are online so you can hear is to ask about the comment I made that we can't just engineer our way out of this. And is there some engineering things that we can use that give us some hope for the future, or are there some behaviors that we can do to change things as we go forward? Absolutely, yes. And so there are a lot of really creative plans for some places in terms of how we can change our land use near the coastal regions to help create buffers, putting in more mangroves and that type of, a lot of the natural buffers that we have removed and that type of thing. And all of those things will help. I was taking the long-term perspective here to say that all of those things only buy us some time from the ultimate problem, which is that it's going to keep retreating. But there's a lot of promise in deploying those, but we also have to remember how we distribute the resources. And that's one of the challenges. If there is no national plan, then it's left to the local level, and it really falls to which are the wealthiest to respond. In terms of behavior, absolutely. The reason this is all happening is because of global warming. And so sometimes when I've spoken to politicians, even in the state of Florida, they say, well, we can't solve sea level rise. Well, you can, because we all need to participate in that process. And from New Zealand, you might say, well, we're a small country. What can we do? A whole lot, because if your goal is over here, if I'm starting a journey, I'm starting a journey soon, I'm going back to Los Angeles. If I don't take the first step in that journey, well, I'm never going to get there, am I? We need to take all the steps, which means we need all the teams, we need all the states, we need all the countries to get to that goal. So in terms of behavior, yes, reducing our carbon emissions and our dependence on fossil fuels is absolutely the most important thing that we can do and should strive for. Yes, great question. Are you calling?
Yeah.
Thank you very much. I'm about 6,000 years ago, sort of halfway between the Holocene period. In Western Pacific, apparently the sea level had started to drop a few meters.
Mm-hmm.
Was that a precursor to the Little Ice Age?
No, and in fact, that has to do with this gravity business that I was talking about before. So there's this thing called the mid-Holocene high stand, which we can explain by changes as the ice sheets melt. The solid Earth deforms as the weight of those ice sheets changes, and the gravity field changes that I talked about with the water being attracted and then going back over here to the far field. So for a while it rises, and then it starts to draw down a bit due to the superposition of all those effects. And so that's basically a geophysical process that's causing local sea level to be different than the global average. And that's really important to remember too when we look at these projections, is that we often talk about a global average, especially in a setting like this, but what people really want to know is what is it going to do here where I am? And that's not necessarily the global average. Today in the tropics, because we're melting both poles at once, if you remember those fingerprints I showed you of the ice sheets, they are highest in the far field when you start to add those on top of each other as you're melting both at the same time. It's the tropics that will take the brunt of it. They will have the highest sea level rise as we melt from polar regions, unfortunately.
Yep.
Simon Upton. I like your first question. I thought we might hear a bit more about the tropics. So could you just expand a little bit? Can you tell us anything about the tropical sea from the record? I mean, you mentioned red bluff, but there must be a hell of a lot of coral out there that you looked at right
Oh,
now.
yes.
And secondly, even if the paleo signal was not so good, what do we know about coral's ability to adapt today? How fast can it cope? and what would we expect to see happening with reefs at different speeds of sea level rise?
Okay, so this question wants to hear more about the tropics. What was the sea level that's happening there and so forth. So I didn't delve deeply into the data that we have, but what we see during the last interglacial period is that sea level does rise, and that's why you see those reefs were building on top of each other in the picture that I showed you over time. But there's evidence, there's several episodes of reef growth, right? And so we actually have kind of these pulses of sea level rise. Now, what's driving that may not be perfectly analogous to the modern day, but it does give us some estimates on these. It's probably capable of having fairly rapid rates of rise as these ice sheets retreat. So that's one thing that we are learning from that. The other thing that we are looking at, and I'm always working with people who are basically coral reef paleobiologists, is to understand how the reefs respond to the sea level rise and the changes in temperature. Those reefs were able to keep up with that sea level rise, and as we see there, because the stuff at the top is growing in extremely shallow water, and so it's keeping up with the rate of sea level rise. They did not get drowned. But the challenge is that the reefs today are not in the same state of health as they were back then. So in fact, when you go snorkeling in the Caribbean, it looks nothing like what we see in the fossil record anymore, because it's been so devastated from many things, from overfishing, from disease, all kinds of things together. That means the reef will not be as able to respond and keep up with the sea level rise, which is a pity because that's a buffer to the coastlines from that wave energy. So as sea level rises, that will leave the coasts more exposed. Now, there are people who are studying this kind of rate of accretion. How quickly can the coral reefs accrete? How quickly are they doing it in the modern day? And there's some debate back and forth about when and exactly they would get drowned, but for sure, their state of health is a concern. And as they continuously are getting bleached now, as we're seeing not just in isolated spots, but almost this kind of pan-global events of coral bleaching, and they die, then they're going to be rebuilding rather than trying to keep up with sea level rise. And so it will look different in the future than it did for this past warm period in that sense.
So I'm just going to ask an online question here from Juliet. Do you think that corals provide enough vertical precision to tell us about sub-metre scale Antarctic ice sheet contributions? So I guess it's really around uncertainties of your coral reefs.
Yeah, and so this is a great question because oftentimes the largest uncertainty in these reconstructions is, okay, well, here's the coral, but where was sea level? Because some corals can grow quite deep and some can grow shallow. And one way to look at that is to look at what species of coral you have. They have different preferences of water depth. We've taken that some steps further to look at the whole coral assemblage, the coralline algae, all the corals, the morphology of the corals. Sometimes they have these very encrusting forms in shallow water. So we're trying to refine that. And it depends on the locality. Some places we are not able to put good vertical precision on. Some we are. So in the Seychelles, which is one of the sites I've been working at, we have found outcrops and corals that tell us we are in less than 2 meters of water. And when we have taken samples from different outcrops on different islands, all the data points plot on top of each other, which means they're not living at all different water depths. They're all capturing this very shallow water signal. So for that particular place, I would say, yes, we are capturing a less than 2 meter scale, and we can use it. But that's not going to be the case for all of the reefs that we study. But something that we really need to be aware of is this vertical precision, and that's something we're trying to make progress on.
I'll just ask one more online question. This is from Paul Bruce. The rate of present warming is phenomenal compared to that of the preceded interglacial periods. Can sudden warming result in different dynamical collapse of the ice sheets?
Yes, I imagine it could. So, and again, this is another great example of why it's not a perfect analogy. And so we always need to keep in the back of mind, what can we extrapolate kind of straight across, right, versus what can we say is a benchmark. So a lot of the work that we're doing is trying to have some constraint on that. How quickly can this process occur? Which right now we can't answer with the ice sheet models. And that gives us at least some constraint on what is physically possible. But pushing them fast, for sure, could end up with a different consequence. There's only so fast, though, that you can discharge icebergs from an ice sheet. And that's where we end up having to rely on the models. And that's the parts we're still working out. So while things are accelerating, they can't accelerate infinitely, is the point. And the question is, how fast can that go? And I suppose the more examples we have, the better we can constrain that.
Is there any other? Yeah,
One over there. on the
yeah,
left.
just over the back there.
The slide with the sea level over time.
It's the tide gauge or the
First one,
not sure which one you want. One of these?
no, one with the
International.
yeah.
Oh, the interglacials way back.
I have two questions about that.
Okay. You want to start asking while I find it?
Yeah.
It's way back in the beginning.
The first one is, for what I understand, is nowadays the sea level increase because of the greenhouse effect due to the carbon emissions.
Yes.
But in the past, it seems that that was not the case because you didn't show. So what was the motive for the island? And then every time you have you reach a maximum, that it falls quite rapidly. It means that there is some negative feedback somewhere.
Right.
So do you think what is this feedback? We know what is this feedback? And do you think when do you think we're gonna have?
Glacial inception,
Yeah.
yes. Okay, so the question is, what was driving this variability in sea level in the past, and how is that different from today? And what is the process that's driving the beginning of these glacial periods, which we call glacial inception? So this 100,000 year cycle is really dictated by how much of the sun's energy is reaching the Earth's surface. So it's small variations in the shape and the wobble of the Earth's orbit around the sun. And that has enough of an effect on the amount of sun's energy that's coming in that it causes these ice sheets to grow and to shrink over time. Now that is different than what we are doing today. Today we have more than 400 parts per million carbon dioxide in the atmosphere. During the last interglacial it was only 280 parts per million. So it was not forced by a higher greenhouse gas concentration. It was these changes in Earth's orbit that were creating the changes in climate then. Right? So that is different. So then the question is, can we expect to go into an ice age soon? And the problem is we have now pushed ourselves so far out of this envelope. If I were to plot on this diagram, this is sea level. If this was CO2, which looks very similar to this graph, and this is here, we'd be like way up here now. And I do have a slide like that, I just didn't include it today. We're off the charts in terms of greenhouse gas concentration. So we were within this envelope where we had this positive feedbacks and negative feedbacks. It kind of kept it within this window. And now we've pushed ourselves outside that we will not naturally go back into this cycle anymore. And so that's one thing that people often ask me. They say, often we hear of these feedbacks and they all seem to be bad, what we call positive feedbacks, which is a terrible word, but it makes the warming worse. Oh, that's this tongue twister too. There are feedbacks that go in the other direction, but they work on much longer time scales. And that's really the big challenge. We are pushing this system so fast, and that's why we have pushed outside of this envelope, is the rate of warming and the rate of change that we're seeing. The coral reefs can't keep up. Those larvae can't disperse to higher latitudes fast enough to migrate away from the hot tropics and that type of thing. Great question.
Okay, I'm just going to ask one more online question because it's quite related to that. What about the impacts of other frozen areas that are melting, such as northern Russia and permafrost? Any studies there or potential future implications?
All right, so there are lots of studies in those regions, and I haven't been doing them. I've been waltzing around the tropical islands, but I do have people who are reconstructing sea level at higher latitudes, people who are studying the changes in the permafrost. There's no question that the high latitudes are experiencing change much faster than the rest of the planet, and it's hard to keep up. It's hard to keep up with the science almost as coming out, as emerging as we're seeing these changes happen so rapidly. So yes, there will be large changes in the Arctic region, in the permafrost areas. Sea level will change there too, and it depends again on which ice sheet contributes to the melting as to how much sea level rise you will see in that region, right? Places that are very close to Greenland have less to worry about from Greenland melting, but more to worry from Antarctica.
Okay, any last questions from the room? Yes, Matt.
Fantastic talk. So I think it was like 2012 or 2013 from the same area you work in Western Australia. There was a study that showed that in the last 100 days, so the sea level rise might have been about 13 metres higher than now. Can you make any comments based on their work, like the rollover?
Yes. So the question is about a study that came out in 2013 in Nature Geoscience by Mick O'Leary, and they concluded that there was a late spike in sea level during the last interglacial. It went up to about 9 meters or so. It was quite high. So part of the reason they got that, they plotted on the graph data from all up and down the Western Australian coastline. And one of the sites that they put on there was that one I just showed you, was Red Bluff, which is tectonically uplifted. And since then, there's a PhD student who's gone through and has demonstrated that the last interglacial terrace itself is warped and has been tectonically deformed. It's not just old tectonics, it's been quite recent that it's been deformed. And so those high points that they have are probably a tectonic artifact and not part of like a global sea level signal. And so I don't think there's any evidence there of a late spike in sea level. Another reason that I say that is the corals at the very top of the outcrop are some of the shallowest water ones. So when we look at the coral assemblages and the morphologies, and there's even these big nodules of coralline algae that only grow out kind of in the tidal range now, that sit right at the top there. So actually it's showing us those were right at sea level. They were not drowned at the end. We see no evidence of that when you look at the reef itself.
I'm going to ask one last question from the online group, and this is probably a loaded question, so don't stroke our ego by answering New Zealand, but perhaps deviating too far from your talk, but hopefully related enough. Are there any governments that you know of leading the way in terms of policy for the required retreat case?
Leading the way on policy. Well, I have been very impressed with what's happening here in New Zealand, and part of my time here has been learning about that. I think we can all learn by looking at each other, though. There's no silver bullet, which someone said before. There's no one way to solve this problem, and how we solve it is going to depend on where we are, too. So one country's solutions will not be the same as another. It depends on where you're starting from and where you have to get to. So I think the point is, though, that we really need to be active in participating in that process and knowing that some of it's going to be trial and error. We can sit around and argue all day and do studies and figure out what's going to be the best way. Well, in the meantime, right, we're fiddling while Rome is burning, yes? So more action is better than none. And some of it's going to be trial and error, and we will learn along the way some things that work and some things that don't.
Okay, so we'll draw the questions to a close. Just want to give a final thank you to Professor Dutton for quite a remarkable talk. So just a round of applause for her there. And it feels weird using your formal title because she's really fitted into the ARC family. She's been here for the last 6 months. We've seen her for about a month. You know, it was a real pity that it did get broken up like that, but we saw each other a lot on Zoom. And, you know, one of your rewards is you're actually supposed to be the 2019 ST Lee lecturer. We were going to have it right at the start of the year. So now you're the lecturer for 2 years in a row. So, you get a double reward there. But yeah, we will be very, very sad to see you go because it just feels like we're just starting to get started on this sort of linking the tropics to these rather more difficult records to deal with in the Antarctic. The tropical coral reefs are beautiful chronologies, very precise sea levels, and we deal with scraps. But we can piece together those parts of the puzzles, and we're starting to get there. So a few more weeks would have been great, but we're certainly wishing you the best in your new job in Wisconsin. Thank you for everyone for turning up at the late notice. Obviously, they were moving goalposts pretty rapidly with this, and we're very lucky to have got to level 1 and have a full, almost a full house with us here. And also a very healthy group online, almost equal number online as well. So just a testament to the quality of the talk and the speaker. The talk was, as I say, it's not comfortable reading, is it, or watching. It takes home to me that point, are we getting near a tipping point? And Andrea talked about these imperfect analogues in the past. They're not perfect analogues. She talked about the ice sheets in the past potentially acting out of phase. And humans have perturbed the system so greatly that it appears they're both going at the same time. So we're doing something nature couldn't do, potentially, which is sort of mad science in a way, but unfortunately there's a lot of people involved in that experiment. So just highlighting also that fact of the rates of retreats is that sort of holy grail we need to get to, and that's where they can really help. Are we looking at centimetres per year? If we get in there, then that's even more terrifying than that final tide gauge that you showed from Florida. So some very important questions, not a perfect analogue, but it helps provide context for what we may be going into in the future. Also want to thank again Dr. Lee Sing Tee for sponsoring this lecture series. It has become an incredibly important part of our academic calendar. As I say, it's just unfortunate we had the delay this year with the shutdown, but it just highlights just how important it is to get into a room and discuss these sort of issues and this sort of science. Also thank you for Tim Naish for really helping to organise your visit here, as well as the logistics around this visit and the lecture. And also thank you to the front staff in the Antarctic Research Centre, so Michelle Dow, and in particular Dow Pasari, for organising the lecture and really setting this all up. And so we've organised some drinks and nibbles upstairs. So yeah, thank you very much for that. So just a round of applause for her as well.